Welcome to today's asynchronous session on simplifying and estimating square roots. Before we begin, let's start with a few definitions. All right, the square root of a number is the value that, when multiplied by itself, gives you that number. So for example, the square root of 25 is 5 because 5 times 5 is equal to 25. So basically we're looking for a number that when I multiply it by its own self is a number. Right? It doesn't mean divide by 2, which is the common mistake. The next thing we're going to talk about is a perfect square. So when you hear the term a perfect square, that's a positive number that has an exact square root, which means that its square root is an integer like 5 or 3 or 2. So the square root of 16 is 4 because 4 times 4 is 16. So we say that 16 is a perfect square. And I'll give you a graphical representation of that in a moment. The radical symbol. So here you can see where I have written a radical symbol. All right, and this, when you don't see any number up on the outside of the radical, means the square root of a number. What I've written here is treat it as its parentheses in PEMDAS, meaning anything that's underneath a square root you have to simplify first like it was in parentheses. And then finally we're going to talk about the principal square root of a number. And the principal square root of a number just means the positive square root of a number. So if you pulled out your calculator right now and you took the square root of 64, it would tell you the answer 8. 8 is the principal square root of 64. Okay, so let's list a few perfect squares. All right, so these numbers that are in purple here are perfect squares. 1 is a perfect square because 1 times 1 is 1. 4 is a perfect square because I have 2 times 2, which equals 4. So remember, they're perfect squares because I'm multiplying the same number by itself over here on the right side. That's what makes it a perfect square. All right, so 9 is a perfect square because it's 3 by 3. Let's draw out what I mean so you can actually see why they call it a square in the first place. All right, so let me take my pen. And let's use the perfect square of 9. So if I draw out 3 times 3, I can draw that as an array of 3 rows and 3 columns. So here we have 3 rows, and here we have 3 columns. This here, how many squares go down or on the length of this? Well, there are 3 squares here. And across its length, we also have 3 squares. So this is called a 3 by 3 square. And if we count the squares inside, we get 9. And notice that this makes a perfect square that is 3 by 3. So that's why these numbers are called perfect squares, because they can be represented graphically as a square. This is in contrast to, say, let me do the number 10, for example. 10 isn't a perfect square because I can't make an array of rows and columns that are the same length. So one way I could make 10 is to have 2 columns and 5 rows like this. 1, 2, 3, 4, I need one more, 5. Right, and we can count that there's 10 little squares in there. But this isn't a square. I've made a rectangle. And I could also set this up to go horizontally so that I had 2 rows and 5 columns, but again, it would still be a rectangle. I could make one really skinny long rectangle of 1 row with 10 squares, but again, you can see that this shape here does not make a square, right? It makes a rectangle. So perfect squares can make squares when we separate them so that they have the same length and width. So you'll get used to identifying these numbers as you work with them more. You know, as I've gone over the years and worked with these numbers more and more, when I see the number 25, it jumps out to me as a perfect square. When I see the number 100, it jumps out to me as a perfect square because I know 10 times 10, in this case, is 100. that makes it a perfect square. So all your perfect squares are you just start with your integers like 1 and times it by its own self, and then 2 by its own self, then 3, then 4, then 5 by its own self, and those numbers are called perfect squares. Okay, likewise, we can talk about square roots. So notice these numbers now in the left-hand column here in the purple. These are the numbers that we were just talking about as being perfect squares. So taking the square root of something and timesing something by its own self are opposites. So when I talk about what is the square root of 4, all right, the square root of 4 is 2, because 2 times 2 is 4. And just to clarify so that we are using the correct terminology that I defined in the beginning of this lesson, 2 would be called the principal square root of 4. All right, there is another number that I can multiply by its own self to get 4 as well. So we know that 2 times 2 is 4, but also negative 2 times negative 2 is also positive 4. All right, so we'll talk a little bit more about that later, but right now you could say that the square root of 4 has 2 answers, 2 and negative 2. However, if you plug in the square root of 4 on your calculator, it's only going to tell you positive 2. That's because unless otherwise indicated, whenever we write the square root symbol out here, we're almost always indicating the positive square root, which we call the principal square root. So here are the other perfect squares. 49 is a perfect square because it is 7 times 7. So the square root of 49 is just 7. So that's what this little square root symbol means. It means I'm trying to find a number that when I multiply it by its own self gives me the number underneath the radical. And they don't have to be whole numbers like this. You know, oftentimes they're not. They're decimals. For example, if I wanted to know what the square root of 3 was. Well, it's not 1 because 1 times 1 is just 1. And it's not 2 because 2 times 2 is 4, not 3. So the square root of 3 is somewhere in between 1 and 2, some decimal. And if you're really interested to see what that decimal is, go ahead and on your calculator and punch in the square root of 3, and you'll see that you get a number that goes on forever and ever, between 1 and 2. Okay, so let's do a few examples finding the square root of a number. Okay, so number 1 here I have the square root of 49. In most instances, when I'm going to write what the square root of 49 is, I'm just going to say 7. However, I realize that in your lesson, sometimes when they ask you to find the square root of 49, they also want the negative answer. They also want you to put negative 7. Typically, this is indicated by them asking you to find the 2 square roots of the number or just find the principal square root of a number. Alright, so how about 121? So let's find the square root of 121. Well, I start going through my integers and seeing if it's a perfect square. And I do in fact recognize 121 as a perfect square. 121 happens to be 11 times 11. So the square root of 121 is 11. So sometimes I get students that get confused with the idea that I am trying to find a number that when I multiply it by its own self gives me the number underneath the radical symbol. So for example, 60, square root of 60. Now, some students will divide this in half and tell me that the square root of 60 is 30. And I want to dispel that misconception right away. Right? The square root does not mean take half of the number. Does not mean divide it by 2. Right? It means I'm trying to find a number that when I multiply it by its own self is equal to 60. Well, some other students will go, well, 60 is 6 times 10, so maybe the square root of 60 is 6, or maybe the square root of 60 is 10. That doesn't work, remember, because we're looking for numbers that has to be the same number that multiplies to be 60. So I want to write out, when I write this equal sign with a slash through it, it means not equal. I just want to point out that the square root of 60 is not 30, so don't do that. And then we'll talk about how to estimate a number like the square root of 60 in a few slides from now. Because 60 is not a perfect square. There's not a whole number, an integer, that I can multiply by its own self to get to 60. All right. Now, in your lessons, you might see questions like this where it says find the two square roots of 16 and find the two square roots of 81. And so when they list it like that, then they're talking about both the positive and the negative solutions. All right, so for the square root of 16, for the two square roots of 16, they might be expecting the answer both 4 and negative 4. Because 4 times 4 is 16, and negative 4 times negative 4 is also positive 16. So how about the square root of 81? Another way they might indicate this is to write both the plus and the minus sign outside of the root. That means they want the two square roots, not just the principal square root. But typically when they don't include that, they always mean just the positive number. So in this case, if I were talking about the two square roots of 81, they are talking about the numbers both 9 and negative 9. Because square root of 81 is 9, because 9 times 9 is 81. And then negative 9 times negative 9 is also positive 81. So let's talk about simplifying square roots that have more than one operation involved. So in the very first slide of this lesson, we talked about underneath that radical symbol, think about as parentheses. So you kind of have to do what's underneath there first. So question number 1 here has the square root of 12 plus 4 all underneath the radical. Since it's all underneath the radical, I need to add this 12 plus 4 together first to get 16. Then we're going to take the square root of 16, which is equal to 4. So you might ask, why not negative 4? Well, unless they indicate otherwise, right, I'm always going to list just the positive square root. So in this case, I would say that this answer was 4. Let's try number 2. So now I have the negative square root of 58 minus 9. So again, I have to work underneath the square root first. And 58 minus 9 is 49. Now I'm going to take the principal square root of 49, which is 7. But then this minus is hanging outside the radical. So it didn't go anywhere. So I bring it down so that our answer is, in fact, negative 7. So why don't we take the moment and pause the video and allow yourself to work out these two examples. All right, so number 1, we get the negative square root. I simplify underneath the root first, and 87 plus 13 is 100. I'm going to bring down the negative because it didn't move anywhere. It's still on the outside of this radical. And the square root of 100 is 10 because 10 times 10 is 100. So we get that our final answer is negative 10. For number 2, remember I'm going to work underneath the radical first to simplify anything that's underneath there using the order of operations. In this case, we only have subtraction, so I'm going to subtract 22 minus 18, and we get 4. Now it's asking me what the square root of 4 is. That means I'm trying to find a number when I multiply it by its own self is 4, and in this case the answer is 2. And notice how I just leave it as the principal square root, positive 2. Unless otherwise indicated, the square root always refers to the principal square root. So how about we do one that's a little more involved? All right, that involves some of the more of the order of operations. So remember, I'm looking at this square root first, and I have to simplify underneath there first if there's anything to do. And then doing square roots in exponents, that's the E in PEMDAS. So a square root in the PEMDAS, the order of operations, is really the same as in exponents, but that will be in future lessons and in future classes. So that really is on the same level as that. And I'm writing out the word PEMDAS here. So I don't have any parentheses. Now I have to do my square root, and I see I have the square root of 256. So I'm going to bring down the 4, and now I'm going to try to multiply that, because remember when we write things right next to each other, it means multiply. But I'm going to figure out now inside these parentheses what the square root of 256 is. So that means I'm looking for a number, remember, that when I multiply it by its own self is 256. I'm not dividing 256 by 2. Alright, so let me think. This is a fairly familiar number with me. I happen to know that the square root of 256 is 16. And yes, indeed, if you do 16 times 16 on your calculator, you get 256. Right? I'm going to bring down the minus 130. Okay, so now I'm still going through my order of operations. So the next step, according to my order of operations, would be to multiply these two numbers, right? We have to multiply and divide before we can add and subtract. So 4 times 16 is 64. So all I did is that part of the simplification, just simplified 4 times 16, brought everything else down. Now finally we have 64 minus 130, so now we can do our add and subtract. And just make sure that you're following the rules for adding and subtracting integers correctly here. I have a positive 64 and a negative 130, so they're opposite signs. So the rules tell me that I need to subtract these two numbers. So I kind of can work out here on the side if I want and take 130 and subtract 64. And this is basic addition and subtraction like you're used to doing. Alright, and I get 66 when I subtract those two. But then according to the rules, I have to keep the sign of the larger number, so we get that the answer to this problem is negative 66. Alright. So let's put that in context of a word problem. So here, how about a square boxing ring has an area of 144 feet squared, or we can also read that as square feet. Okay? So whenever you see something being raised to the second power there, right, that means we say squared, or this means square feet, or we know that we're talking about an area. So in this case, we have a two-dimensional boxing ring and it has an area of 144 square feet. We want to know what the measurement of each side of the ring is. Alright, so let's think about this a little bit. It tells us it's a square. So I'm going to go ahead and draw out a square. And it tells me that the area inside the square is 144 feet. And what it's asking me to figure out is the length of each side. Well, if this is a square, as it says here, each side length is the same. Alright? So this side, whatever this question mark is the same length as this side. So they're really asking me, can I figure out a number? Remember, these question marks here are the same number because this is a square. So when I take a number and I times it by its own self, I want it to equal 144, because remember, that's how we find area. When I'm finding the area of a rectangle, I just multiply the length times the width. And in this case, the length and the width are the same number because it's a square. So that's telling me that if I know the area of this square, then all I have to do is the opposite is taking its square root to find out how long these sides are. Because that will give me a number that when I times it by its own self is 144. So it's really the same thing as saying, can you figure out what the square root of 144 is? And if you didn't know, you could go through and you could plug it on your calculator and you'd get the answer 12. Now always when we're working with word problems here, we need to include the units. So this area here is in square feet. So I would say that each side of this square is 12 feet long. Remember, not 12 feet squared, because squaring is an area. And just feet is a length, right? How long is the side of that ring? Well, it's 12 feet. All right, so let me go back one, as I skipped one of these word problems. Let's take a look at another example. Okay, so suppose a student has 45 little square tiles, and he wants to make the largest square possible. How many square tiles can he use? All right, so we have square tiles, and we want to make a square. And again, when we say we want to make a square, one second. When we want to make a square, the length and the width have to be the same number. So the number of squares that we put across the top of this thing and the number of squares that we put along the side have to be the same number. Now I notice that I can't use all 45 squares. I can't use all 45 squares because, excuse me one second, I can't use all 45 squares because 45 is not a perfect square. And I know that the slideshow just went off for 1 second, but give me 1 second and we'll keep thinking about this problem. So think about your square and think about how many little squares you could use out of that 45 so that you make a perfect square. So we don't have more than 45, so what you should be thinking to yourself is, how many squares can I use to make a perfect square? So that's like asking for a perfect square that is less than 45. One moment, and the PowerPoint will be back up. All right, I apologize for this. Okay, so let's draw it out. All right, so I'm looking for the perfect square that's just a little bit below 45. So I start going through my numbers. 5 times 5, that's 25. Can I do more? Let's see, 6 times 6 is 36. Okay, I definitely have 36 squares. How about 7 times 7? That would be the next perfect square I can make. Wait, but 7 times 7 is 49, and I don't have 49 squares. I only have 36 squares. So if I want to make this thing a perfect square, the most I can use is 36. And each side would be 6 by 6, so we would have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And then that would be 6 columns down. And I know I don't have a perfect square here because my drawing isn't perfect, but if you count the number of squares I have in there, there are 36. And in this case, I would have 9 leftover squares. If I really wanted to, I could make a little tiny 3 by 3 out of the remaining ones. So I could make 2 squares, one a 3 by 3 and the other one a 6 by 6. Let's talk about estimating a square root without a calculator. This question here asks me to find 2 consecutive whole numbers that the square root of 58 lies in between. Alright, so I start going through my list of perfect squares. Alright, so I'm trying to think about what 2 numbers multiply to give me 58. Right, and they have to be the same number. So I kind of start making my list of perfect squares. So I start going through and I notice that 36 is a perfect square because 6 times 6 is 36. 7 is a perfect square because 7 times 7 is 49. But that's still too small, right? We want this to be the square root of 58. So 7's too small. Then when I try 8, I go 8 times 8 is 64, so the square root of 64 is 8. Okay, well that's bigger than the square root of 58, right? So I notice that the square root of 58, if I'm looking at my list here, falls in between the square root of 49 and the square root of 46. Alright, so that means that the answer to the square root of 58 is somewhere in between 7 and 8. So if the question is just asking me what two whole numbers does that lie between, the answer is 7 and 8. This answer is 7 point something. And then since 58 is a little bit closer to 64 than it is to 49, I know that it's like probably more than 7.5. You know, I might guess 7.7. Right, so if I want to find two consecutive whole numbers that the square root of 24 lies between, I'm looking at my list of perfect square roots here. And I notice that square root of 24 lies between the square root of 16 and the square root of 25. Right, that means that this answer is somewhere in between 4 and 5, because the square root of 16, right, is 4, and the square root of 25 is 5. Now, take a moment to think to yourself, is the square root of 24, is that number going to be closer to 4, or is it going to be closer to 5? Right, and as you can see, 24 is only 1 away from 25, so I bet this number is really close to 5. And since it's in between 4 and 5, I might guess like 4.9. And if I really wanted to check how close I was, then I would take out my calculator and multiply 4.9 times 4.9 and see how close it was to the square root of 24. So let's pause this video and go ahead and answer these two questions. I want you to find two consecutive whole numbers that the square root of 65 lies between. And then find two consecutive whole numbers that the negative square root of 8 lies between. Alright, so for the square root of 65, I go through my list of perfect squares, and I see that the square root of 65 is in between the square root of 64 and the square root of 81. You could also think about this in the reverse way. You could start going through the whole numbers. For example, I could go 7 times 7 is 49. That's a lot smaller than 65. 8 times 8 is 64. Oh wait, that's really close to 65. And then I know 9 times 9 is 81. So I can stop there and say this number is somewhere in between 8 and 9. And a lot closer to 8 than it is to 9. Alright, so here I'm saying the square root of 64, that's 8. Square root of 81 is 9. And so the square root of 65 is somewhere in between those two whole numbers. A lot closer to the 8 than it is the 9. I'll try the same thing with the negative square root of 8. So I'm thinking right now that the square root of 8, now remember we're on the negative number line, I'm trying to think of the whole numbers. Well, 2 times 2 is 4, that's not 8. 3 times 3 is 9. Oh wait, that's a little bit bigger than 8. So this number is somewhere in between the square root of 4 and the square root of negative 9. Both negatives, right? We're on the negative side of the number line now. So this number is somewhere in between negative 3 and negative 2. Right? On the number line it would look like this. It's negative 1, negative 2, negative 3. And remember, the square root of negative 8 is a lot closer to being closer to the square root of negative 9 than it is the negative 4. So if I had to pick a place where I thought this was on the number line, I think it would be right there, right before negative 3. So now let's talk about getting a more precise answer by estimating than what I was just doing. So before I was noticing that it's somewhere in between these two whole numbers, but probably closer to this whole number. We're still going to use that same philosophy to calculate the square root, in this case of 83, to the nearest tenth without a calculator. So first I want to figure out what two whole numbers it lies between. So I start going through my perfect squares. And I go, let's see, 8 times 8 is 64. That's too low. Remember, we want it to be 83. Then we go 9 times 9 is 81. Oh, that's still too low. We want it to be 83. We just did 9 times 9. Okay, next one. 10 times 10 is 100. Okay, that's more than 83. So now I know that the square root of 83 is in between the two perfect squares of square root of 81 and the square root of 100. Right? The square root of 81 is 9, and the square root of 100 is 10. So this number is somewhere in between 9 and 10. But we're not done answering this question because they don't want to know what two whole numbers it lies between. They want to estimate this to the nearest tenth. Okay, well, just because 83 is a lot closer to 81 than it is 100, I'm guessing that the square root of 83 is just a little bit bigger than 9, but not too much bigger than 9. Maybe it's like 9.1 or 9.2. So is what I would do at this point is I would say, well, let's go ahead and let's guess 9.1. So this is the part where you have to guess a little bit. So I'm going to take 9.1. I'm going to multiply it by its own self. Remember, because we're looking for a number that when we multiply it by its own self is 83. So if you really want, you can pull out your calculator and go 9.1 multiplied by 9.1. And when you do that, you get 82.81. 82.81. That's really close to 83. But let's see if I can get even closer. Maybe I'll try next 9.2. Remember, I'm just trying one place past the decimal point because it says round to the nearest tenth. So then I go onto my calculator and I would try 9.2 times 9.2. And when I do that, I get 84.64. Okay, so I'm trying to decide which of these numbers is closer to 83. Well, 82.81, that's only 0.19 away from 83. Less than 2/10 away from the number 83. Whereas 84.64 is 1.64 away. So you could subtract the two numbers. That's basically what I just did. I subtracted 83 minus 82.81, and I got 0.19. Then I took 84.64 and I subtracted 83 and I got 1.64. Well, 0.19 is the winner. It's a lot closer to 83. So now I'm looking at 9.1, right, as being the square root of 83 rounded to the nearest tenth. Right? And if I had to go further decimal places than that, then I could. After that, I would try taking 9.15 times 1.95 and seeing how if I got closer to 83. So you could carry that process out forever, and that's what they had to do before they had calculators. All right, how about we estimate the this square root, negative square root of 22 to the nearest hundred. So you can start going through the perfect squares in your head again. 4 times 4. That's 16. That's a little too low. We want it to be 22. 5 times 5. Well, that's 25. That's a little too high. So we know that the square root of 22, if I'm writing it out, is somewhere in between. And when I write these inequality symbols on here, it is a range. What's on the left is the low side, and what's on the right is the high side, and this one's right in between it. So square root of 22 is somewhere in between the square root of 16 and the square root of 25. Remember, I'm not putting the square root of 20 out here, the square root of 21, or the square root of 23 over here, because I want these numbers to be perfect squares. I want them to have whole number answers, right? So that way I know where to estimate it. So I know that the square root of 16 is 4, and I know that the square root of 25 is 5. So I know that the square root of 22 is somewhere in between 4 and 5. Then I look at what I wrote originally, and I kind of use the idea, which one is it closer to, this number is closer to get an idea of it, where to guess first. And since it's closer to 25 than it is to 16, I'm going to guess that this answer here is somewhere in between 4 and 5, right, but probably greater than 4.5, which would be right in the middle. So maybe I guess 4.7. I don't know. I'm going to guess 4.7. And so I go into my calculator and I multiply 4.7 times 4.7. And when we do that, we get 22.09. And now I know that my guess was really close because I'm only 0.09 away from 22. So I really don't think I'm going to get any closer than that, but I should check just in case. Notice that 22.09, that's a little bit higher than 22. So if I'm trying to guess this one now to the nearest hundredth, I could see if it's 4.6. If I'm going to the nearest tenth. We will go to the nearest hundredth though on this problem. So if I do 4.6 times 4.6, now this is where the little bit of trial and error comes in, I get 21.16. Okay, so we can see that 22.09 is a lot closer to 22 than 21.6 is. Alright, so it's not 4.6 something, it's 4.7 something, or it's a little closer. So now if I really want to estimate this one to the nearest hundredth, I can take 4.7, and I know that that was a little bit too high, right? Because remember, this answer we got for that was 22.09, and we want it to be 22. So maybe I'll guess a number just slightly lower than 4.7. How about 4.69? So that was just 1/100th less lower. So then you can go on your calculator, and this is what you'd have to do. You'd have to go 4.69 times 4.69. And when I do that, when I multiply 4.69 times its own self, I get the answer 21.99. 9961 is actually what I get. Oh wow, that is really, really close to 22. So now I know that if I'm estimating the square root of 22 to the nearest hundredth, two places after the decimal, it is 4.69. And just to check that, whenever you check that, let's bring over our calculator here. What is the actual square root of 22? And in this case, I forgot to mention, in this case here, we have a negative out in front. So if I'm estimating this to the nearest hundredth, I would say that it was negative 4.69. And like I was pointing out before, you could always check this on a calculator, because I could go in and I could punch in 22, take its square root, and then see what the square root of 22 is. It's 4.69014. So our estimate, doing this by hand, was very, very accurate to the actual value, right? And this value actually goes on forever. So that concludes today's lesson. If you did not attend the synchronous session and you're watching the asynchronous session here, you need to go back into the course notes where you found this video, the course announcements, excuse me, and answer the asynchronous questions 3. So underneath where the asynchronous session course announcement is, there is a link that says questions asynchronous session 3. Click on that link and answer the question on the Google form and make sure you submit it.